Hello and welcome to our second part of our economic and social well-being workshop, in which we're going to use a simplified example, or we're going to reiterate the simplified example, but we're going to walk through it using ArcMap to generate the various surfaces. And to begin with here, we should make sure that we've already done the appropriate first steps of downloading and unzipping the workshop file, and additionally installing the Armorous Raster Utility Toolbar. If you have not done so, please go and download the workshop file and the toolbar from either the team site or from the links provided here. And once they're installed, or once they've been downloaded, simply double click the add-in toolbar, such as seeing right here, and at the same time make sure to unzip the files within the workshop folder, which when unzipped will look like such. There should be a folder that says data, a folder that says models, and a folder for output surfaces, in addition to a delivered cost workshop MXD. The data sets that are within the data folder itself will include Tiger roads, national hydrological data streams and water bodies, which we're using for barriers, a fishnet command output, which we're using for the land management units to summarize our surfaces for SysX, in addition to a series of raster surfaces from the imputed FIA plots, which quantify basal area per acre, trees per acre in tons. And then finally a national elevational data set, DEM. And just to remind everybody, what we're really doing in this context is defining our delivered costs, and in addition to our desired conditions for removal, the revenues that we would see from that removal, the cost associated with implementing those prescriptions, and the income. And then finally, we're going to get at summaries at that LMU level. We're going to be using the delivered cost model and the form for inputting data so that we can get at how much it would cost to move material to the American wood fiber, just like in the Part 1 example. And we're going to use batch processing to create a series of desired conditions that are realized as a raster or a function modeling raster data set. Next, we're going to use revenue costs, or we're going to calculate revenue, costs, and income from those data sets using batch processing. And conceptually, all we're doing is subtracting revenue, or subtracting costs from revenue to get at what the income is through these batch files. And then finally, we're going to summarize this information up to each of the LMUs, in this case, a 50-acre square represented by that fishnet command. And for that, we're going to have three separate values: a cost, a stems per ton, and an income. And those will then represent the inputs into SysX to be optimized or used as constraints. So let's go ahead and begin. And to begin with that, let's open up ArcMap and load in the delivered cost workshop MXD that's found as part of the workshop. And within the MXD, there should be a series of layers that come up from the very start. It says facilities, which represents the conversion facility, American wood fiber conversion facility, that we're going to move materials to. Stanislaus Forest boundary by this orange polygon. A road network derived from Tiger, where we have kilometers per hour that we're moving. These numbers are put in kilometers per hour because the elevation model's in meters, and so we just keeping like units. However, we could have calculated these in miles per hour. We've got some other variables in here for a more complex example, which will be part 3 of the workshop. But we also have barriers included in the landscape that are derived from the streams and NHD water bodies. And then finally, we have our LMUs, which are a whole bunch of little squares across the area in which we can summarize those values into a vector format that can be inputted into for SysX. Now, I don't want to confuse anybody. These are not the LMUs that Carlos is working on, but these are just for this demonstration. So the first step in this modeling process, if you recall back to the first part, we had multiple steps. We had a step where we were calculating the desired condition and a step where we're calculating the delivered cost. Because those are independent, it doesn't matter which one we run first. We're going to go ahead and calculate the delivered cost if material existed on the landscape, given the various topographic aspects of the forest and infrastructure that's on that forest. To do that, the very first step is to run the delivered cost model. Now, if you've clicked the ArmorS raster utility and we've installed it, and if you open up raster analysis and scroll down, you will not see all the values that are all the different tools that I'm showing on my screen. That's because the majority of those tools are not loaded automatically. Instead, you have to customize the toolbar and go to the Commands tab and select each of the tools that you want to load in there. The reason not all of them are loaded automatically is because many of the tools are not documented, and this is one of those tools. And so if we navigate to raster utilities, lowercase, and we scroll down to the delivered cost model, we can drag it and drop it anywhere within that raster utility. Since I already have it there, I'm not going to put it there, but go ahead and drag and drop it to that location for this analysis. Once that's done, now when you click the drop down, you have the delivered cost tool. Upon clicking that delivered cost button, we need to select our digital elevation model as an input. Make sure our speed units are in kilometers per hour because our roads have a kilometers per hour field that we need to specify. We want to specify the location, the facility's location. And in this case, we only have one facility shown. But if we wanted to plug in 3 or 4 different facilities, the algorithm would find the least cost path anywhere on those cells to those facilities. If we wanted to look at it from a perspective that one of the facilities we're going to send dimensional lumber to, another one we're going to send chips to, we can run this model multiple times to get the cost to deliver anywhere from the Stanislaus and the surrounding area to that facility. Let's go ahead and plug in a $1 per hour rate for our semi-truck driver and machine at $95 per hour. And remember, our payload in this context is in bone-dry ton because our estimates of forest characteristics from Karen et al. Imputed FIA plots is derived in bone-dry tons. For our off-road scenario, we're going to look at a very simple case in which it's just a tractor-based skidding system. And we're going to estimate the speed of that tractor-based system at about 5 kilometers per hour, which is roughly like 3.5 miles an hour. And a machine rate of somewhere around $85 per hour. Here again, in terms of bone-dry tons, only 4 tons. Next, we're going to specify barriers to motion. These represent streams, perennial streams, and water bodies that we can't skid across to bring material on the ground to a given road surface. We're going to plug in an operations rate of $15 an hour, which includes felling costs. This may be high or low, but we can spatially depict these. Right now, I'm just going to put in a constant number. Similar with our off-road, we could spatially depict it as a raster based off a series of queries, which we're going to get into in part 3. But for the simplified case, we're just using constants. And we're going to add in another 75 cents for administrative costs based off $1 per ton, just to make sure that, across the landscape. Here again, this can be a very spatially explicit rendering of the dollars per ton, and or we can address it in terms of acres and use batch processing, which we'll get to here in just a minute. We're going to specify an output location. And in this case, we want to go to our workshop folder where we've extracted all of our information. For me, that is in R5 Fire and workshops and delivered cost, output surfaces, and we're going to select travel times 1, which should be in your workshop folders. Now, if you notice, this says File Geodatabase. In previous renditions of this tool, I made it so it only could store within a File Geodatabase. Since then, I've updated it so that it works off of file systems, but I've not updated the label. So when you see File Geodatabase, recognize that that's because I've been lazy and haven't updated my code. Upon selecting all these values, we can then hit the execute button to get at what is that delivered cost, giving all these different settings in the variable to move material to this facility. Now this will take just a few minutes because it's going to actually be calculating in an iterative fashion every combination of cells to move material to the closest road segment and the cost along that road segment to get to the American wood fiber conversion facility, in which case this is a fairly substantial analysis. And the tools that I've developed really speed up the processing step here and reduce the overall cost, but it's still, or the overall processing time, but it still does take a few minutes to process. And so while this is running, we'll discuss some of those various inputs and conceptually talk about how things actually are being processed in the background. So if you will, imagine a skidder down in the lower portions of the Stanislaus. And if that skidder was trying to move material from there to the nearest road segment, which would be that nearest road segment? Would it be here, right off of here, and down along these lines till we get to the main road section so that we can get to the mill? Well, it's not in this algorithm, it's not only calculating the least distance, it's also calculating the travel times that are associated with that distance. So it's getting at how, not only how far is it moving, but how fast can it move? And not only how far and how fast in two-dimensional space, but how far and how fast in three-dimensional space to move that material from this location at every 30 meters all the way to the American wood fiber facility. And it does this simultaneously for all 30-meter cells within the forest. Once those travel times are calculated, we then use the machine rates and the payloads to get at what that dollar per ton cost. And we can see for the entire Stanislaus at 30-meter resolution, it takes roughly 2 minutes for this process to occur, and calculate what that delivered cost would be. Now, the output of this is created as a function raster, meaning it's not stored permanently to disk. So at this point in time, we're going to go ahead and permanently store it to disk. Now we can use Esri's save function, or we can use the save function I have created to save this disk, or save this raster to disk. And in this case, I'm just going to go ahead and export it using Esri's save function as a surface. We need to specify an output location, and I'm going to specify our travel times 1, and we're going to store it as a TIFF. And what the output of this is the dollar per ton at every given cell if there was any sort of material being moved off that landscape. We'll hit save, and that will store this temporary raster into a permanent format so that we can view and use throughout. We didn't have to do this, but I did this specifically so that you could see how these outputs might look. I'll go ahead and remove the previous surface, and now we can display and use this in any way that we want, just as if it was a regular raster. We can look at the low and high cost areas, calculate it in terms of standard deviations, and I can go ahead and turn the LMUs off, and then we'll zoom into one little area just so we can kind of look at the level of detail that we have. I'm going to also change the order of rendering so that we can see it sitting on just on top of the elevation model. And let's just zoom into this area here. And what we see is that with regards to the roads, areas near roads are less expensive to move material to the American wood fiber facility. We also see, though, that there's a compounding impact of where the stream channels are with regards to those roads. For example, it would be extremely easy to move material from this road segment from this location to this road segment, but we can't get it to that road segment because we have a barrier. So instead, it's being moved to this location right here, which then it's along the road to the main road artery over here. And so what we actually are getting at is, what is the specific cost to move material given the infrastructure on the landscape and the speed at which things can move along that infrastructure with real barriers to motion, such as stream channels and roads. And what we can quickly take from this is there's some areas across the landscape that are simply too expensive to ever move material across the landscape. It's $230 a ton to move it over here, unless we have a gate price of somewhere around $230 or $240 a ton. It's not economically feasible to ever move that material to the ground unless we change the existing road infrastructure or we put new roads in that area. But this represents the potential. What is the cost if material exists on that landscape? To get at what is the cost given our prescriptions to bring our forest to a fire resilient condition, we want to kind of look at how much is on that landscape. And in order to do that, we're going to use those basal area and trees per acres, but we're going to also use batch processing. And so we're going to look at what is the correct syntax to make that happen. And I've already written these up as batch files, but what these batch files really represent is a language I developed that is a command-driven language that combines each of the functions within this batch processing into a series of commands, one of which, in this case, if we're defining those restoration areas, or if you recall back to the first part of the workshop, areas that have 165 square feet or more basal area, what this batch file is doing is opening all of our pine basal area surfaces, our hardwood basal area surfaces, our tons of above ground biomass for pine, tons of above ground biomass for hardwoods or needle and broadleaf. And then we're doing a series of arithmetic analyses to get at the total basal area for any cell, the total tonnage for every cell, the logical argument that says once we have that total basal area, we want to find all the areas that have at least 165 square feet of basal area. So we're using a logical term that says total basal area and greater than, that's what the GE stands for, 165 square feet. 165 square feet. And then we're going to multiply that output by the total basal area. So to step back for just a second, the output of a logical argument is either a 0 or 1. And so all the conditions that are true have a 1, or all the conditions that are false have a 0. So when we multiply that, what we're identifying is how the areas that have basal area and how much total basal area they have. Our next step then is to define how much of that basal area is related to the total basal area, or how much of the 165 square feet is related to that total basal area, and use that proportion to get at the total amount of tonnage that will also be removed, being directly related to the basal area that's being removed. Now, this can look a little scary, and there can be a lot of questions related to how do I write this coding? What do I even learn in here? And to facilitate that, there's a batch processing tool that helps you write the coding. In which case you could use something like dollars per ton equals, or let me back up here. We can say a new output JKL equals an arithmetic analysis, which uses dollars per ton, putting in parentheses here, and in order to, the inputs are delineated or delimited by semicolons, dollars per ton times 2, and then an operation of ESRI raster multiply. And this would create a new raster function model surface that has dollars per ton times 2. For any one of these functions within batch processing, you can select on it, and we'll use the logical function. Click on syntax, and you can look at the input. In this case, it's saying an input raster 1 or an input raster 2. These could also be constants, and the logical operator, whether it's greater than, less than, and so on and so forth. For our purposes and for this workshop, what you guys are going to do is highlight the location of the soft basal area and point to it specifically on your computer. Once these are created, the final output there, I shouldn't have closed it so quickly. Give me just a second here to reopen that. The final raster surface that's created, total tons, when run within my tools, will be displayed in the table of contents. And to illustrate that, I'm going to just open up that file, and we're going to look at raster areas using this plus tool that looks like almost an atom. So it's an add-on to the regular add layer tool. And we're going to load in restore areas. As we can see, ArcMap is now processing all those commands, and we now have an output raster that's total tons. Now this is not a permanent raster. This is a temporary raster, a function raster. And we can specify, we can use it as if it's any regular type of raster. We can display it, set what the standard deviations, and process it as if it's a raster and look at it from a display perspective. And as we're rendering it, we can now see what those different values are. I'm going to turn off some other layers so that we can see this better. And change the rendering so that we have something more familiar that we're looking at. It looks like a gradient. And then let that go ahead and draw. Oh, I guess I have to refresh. So now we can see the areas that are in purple have a low total tonnage that we're going to be removing, where the areas in darker green have a higher amount or higher tonnage that would be removed. So we can zoom in and we can start getting an idea of the detail that we're talking about. In this general vicinity, there's a great deal more tonnage. We can look at the information, how many tons at any one of these cells. In this case, 40 tons that would be removed to meet our desired condition. 57 tons, and so on and so forth. Now we can build off of each of these surfaces, so we can define the conditions in which we're looking at just the restoration of the stem. So in this case, we're not taking total soft basal area, we're just taking the stem tonnage. We can look at the costs, which is associated with this, which our first notion is that one of the open rasters refers to a batch file. So we can include batch files into our batch file, into a different batch file, so that we can build upon our analyses. And in this case, to use this tool, to use the cost one, you'd simply highlight it, change the directory path so it points to the correct location where you unzipped the work file projects, and change that for each one of them where it's specifically defined there. And then the same syntax would work to define what costs we're at. When we want to look at income, we can see that income is pulling the cost function and the revenue function. We can look at what's included in the revenue function. And the revenue function we're simply opening up the restore area stem batch file, or the boltons, and we're multiplying it by $32 per acre. Now we could use this $32 per acre, or we could use a spatial rendering, saying that in some locations we're going to get more for our dollar than others, and that might be, or more for the tonnage than in other locations, and that might be applicable to say we have a different product type coming out of some locations versus another. But each of these can be loaded directly into our table of contents, and we can, at any given time, just like so, and used as if it was a regular raster surface. And so in this case, I'm going to show the income. What's the combination of the revenue versus at $32 per ton versus the cost? And we're going to look at, we're going to invert this. So green areas will represent low cost, or high income versus expensive areas across the landscape. And so when we display this, we can now get a better idea of what the cost would be, what the income would be for any given location. See, we'll zoom out to the rest of the landscape. And what we can see is that there's areas that are relatively close to the conversion facility that would represent positive income, versus areas that are further away, which would represent a cost to actually implement the prescription on the landscape. Our final step is to use zonal statistics to relate our cell values to our LMUs. And in this case, we probably want to extract or export our income into as a file. So I'm going to go data, export data, and I'm going to store this in my output folder, travel time 1, and call it income and hit save. This will take just a few seconds to process and save that raster to a permanent format. And the reason we're doing this is because there's, in terms of memory, this would take a great deal more memory to process than if we just store it and then read it directly in. I'm going to hit yes at this point and load that into the system and remove the previous one. I don't really care how it's rendered, because that just doesn't, that's not going to make a difference. But I am going to add in our cost surface and do the same thing, export that as a raster. And I'm going to export that again to the same location, and I'm going to call it cost. Hit save. And it'll take just a few seconds to serialize or make it permanent across that landscape. And we can add that into the table of contents. I'll go ahead and remove it, just remove the function model version of it, just so it's easy to keep track of. Total tons, let's see, I don't need to have that in there. We want to also add in revenue, in which case this is how much, given at $32 per ton, we'd expect to see at any given cell, every 30 meter cell. I'm going to also export that data and just call that revenue. Now, once these three surfaces are created, these are going to represent our inputs into ForSys X, or the fields that we would use for ForSys X, that we would optimize or build in as constraints. We could add other variables too, but for this example, we're just going to use these three. But once we have those, what we also want to do is turn them into a composite, or a multi-band raster data set. So we're going to look at our first band being cost, our second band being revenue, and our third band being income. And we'll call this cost, revenue, income, or CRI for short. And this is going to be what we want to summarize each one of our LMUs by. So as we view, I guess before we do that, we can just look at what this looks like in a 3-band rendering of it. And we can see there's a lot of pink areas, which means it's relatively high cost, but we can also see that there's blue areas in terms of the income, or shades of blue, in which those areas do bring in an income, and so on and so forth. And now what we want to do is summarize using our zonal statistics. In our zonal statistics, I'm going to go ahead and zoom into one area just so we can get a better idea of what's going on. For every single one of these polygons, these square polygons, it's going to summarize the cells that are inside that polygon, and then in another process attribute that zonal value to each individual cell. Now we could do this as a batch process and write the code to make it happen, or we can use the RMS raster utility and manually select each one of these inputs through the GUI interface. So our zone raster represents our LMUs. We're going to use the OID field. We're not really interested in averages in this case. We really want to sum it up, remembering that our estimates are now absolute values because they've been transformed in our batch processing to those absolute values. So every cell, this is the cost to implement on that cell. It's the revenue that we would get from that cell, or it's the income that we'd get from that cell. And then our value raster that we want to select is our composite, our CRI surface. And we want to specify an output folder. Now I'm going to use our status ecosystem, and I'm going to call this LMU stats 2 because I already ran this beforehand and it's part of the data set. If you guys want to look at what these, if for some reason an error occurs or something like that, we're going to hit save, and we're going to hit execute. And so here, for every single one of these cells, this tool is extracting the raster values within that and summing up those values to give us a total value for each one of those cells. And this will take a few minutes, but should process relatively quickly so that we can get at what those values are. And this really represents the last little bit of this simple example, and demonstrates how we can take those raster surfaces that we built from the delivered cost modeling and the prescriptions and revenues and so on and so forth, using batch processing and the RMS raster utility tools, and manipulate that raster data so that it can go into a vector format for using in ForSysX. The process should be finishing up here in just a minute, and when it does, we'll look at the table that's calculated. And I guess before we end this part of the workshop, we'll look at one other tool that is applied to attribute each one of those values into our raster surface. The tool is now telling us that it's made the VAT file and it's populating that VAT file, and we're now finished, and we have a new data table that is LMU stats 2 VAT. If we add it to our table of contents and open it, what we see is that we have a table that has an object ID, the band in which, whether it was cost, revenue, or income, band 1, 2, or 3, the zone that it came from, or the OID of the polygon, how many cells were in that polygon that were not null, and then what was the summed value. And as we scroll down, we see some cells had negative values when they're added all up, and some cells have positive values, and we can now display that for our LMU accordingly. But in order to attribute our LMU, we have one final tool that we need to use, which is format our zonal data, in which we can specify our LMU as our zones, our link field, which was OID. We can give it a prefix such as CRI, and then our stats table that we just created. So that's located in this database right here, IMU stats2, and it's wherever you saved it. And if we hit execute, which I've already executed ahead of time, we'll end up with 6 new fields that say the count of the cells for each one of these fields. And then since it's band 1, here's the cost field, the revenue field, and the income field. And then we can look at each one of those values. And using that, we can then display our cell value, our LMUs, based off of quantiles. And we can look at our income. I'll hit OK there. And let's say we break this into 10 categories. And we can look at where the expensive areas are versus the least expensive areas. I'll turn off our CRI field and we'll zoom to the extent of the layer. And we can even go a step further and display this. I'll turn off some of the other layers here so that we can see. But in symbolizing this for a vector field, we can select all values. We can look at the expensive, we can flip the symbols and get rid of the outline for each individual land management unit. And now we can visualize where it's expensive, red areas, and where it's cheaper, or where we have more income coming in, the bluer areas. And with that, that ends our first example. Join me for the third part of this workshop, where we look at manipulating the costs and rates based off of the topography of the landscape for each one of these variables, and basically do the same thing, but spatially depict many of the inputs that we were putting constants in previously. Thank you much.